Hello everyone, my name is Girish. Today I'm going to teach you about unbalanced and balanced trees. So basically, let's first understand what a tree is. A tree is basically something you must probably be knowing. It's something that goes from a root and keeps branching and keeps branching and again branches and branches and branches till infinity. Okay, so now what happens in a binary search tree is we have a root and all the stuff on the left side of it is smaller than it. All the stuff on the right side of it is bigger than it. So that's a binary tree. Next, so these are just the introduction to the basic concepts. So now I shall move on to a balanced and an unbalanced tree. Let's assume a list of numbers 1, 2, 3, 4, 5, 6, 7. Now, if you draw a normal binary search tree for this, what happens? You get this, and then 2 is greater than 1, so it goes to the right of 1. 3 is greater than 2, so it goes to the right of 3. 4 is greater than 3, so 4 goes to the right of 3. 5 is greater than 4, so it goes to the right of 4. And so on, you get 6 till 7. So, however, if it was something like 4, 3, 1, 2, 5, 6, 7, then you get one number going to the left, then one going to the right. So here you get 1 to the left, and then 5 comes to the right of 1. So you have much more spacing between the numbers. So what you ideally have to achieve is something like this. Something like this. This is what we want to achieve in a binary search tree when it's balanced. Because when it's balanced, the number of traversals you need to ultimately get to the leaf, the maximum number of traversals you have to go before you find a leaf or any node you're searching for is log n in that case. However, in this case, it is n because you have to go 1, 2, 3, 4, 5, 6, 7, n times. In this, it's log n times. That is the number of times the tree is branching. So that is clearly log n. That means log 2n because that's the number of times it's branching. So now, how do we convert a tree like this to a tree like this? We do this by balancing. This is an unbalanced tree and we convert it to a balanced tree by using 2-3 trees or AVL trees. So let me go to an approach called 2-3 trees. In a 2-3 tree, the possible nodes we can have are something like A, B, C. This is one type of subtree we can have, or we can have A, B, and then C, D, E. So in this kind of a node, B is less than A and C is greater than A. In this kind, C is less than A, D is in between A and B, and E is greater than B. So we form a tree based on these kind of nodes, either 2-node or 3-node trees. So now moving on to the example we took earlier, 1, 2, 3, 4, 5, 6, 7. So one important rule, which we must always follow: anything you insert must be at a leaf. This means you can never insert at anything other than a leaf. So always insert at a leaf. So going on, so first when you have nothing, you don't have a tree initially, then there's no leaf. So you just have to insert one directly. And then you can insert a maximum of 2 nodes as you see here. So now what we do is we add one more here itself. The next one we add it here itself because this is the only leaf. A tree with only one node is a leaf. It's a leaf, it's a root, it's a tree, it's everything. So now after we have this, now when we want to insert the third number, 3. Now we realize that this kind of tree is not allowed anymore. So now what we do is we split this into 2, 1, 3. This happens only for the parent node, this kind of splitting. So because the parent as in the root, so we split it like this and we get 2, 1 and 3 like this. So now moving on, now the next number we have to insert is 4. As I said, focusing on the key rule, anything you insert must be at a leaf. Must. Because if you go wrong with this, your whole 2-3 diagram is going to go wrong. So this is a very essential condition to ensure that you're going right in whatever you're trying to do. So now we want to insert 4 next. So you put 4 here because 4 is greater than 2 and it's greater than 3. So it belongs in this particular node. You always try to form, 3 node trees by expanding those 2 node ones. And then next you have 5. So now 5 goes here. Now again we have a big problem here. Again this node is overflowed now. Now how do we handle this problem? This is a calamity of massive proportions which we need to address with proper techniques and algorithmic approach so that we can handle these problems in future and so that they don't affect our complexity too much. To do this, we again split the node. But this time, we send the middle of the overflowing node to the parent. So we send 4 to the parent. And then we put 3 here and 5 here. So as I explained in this part, I'm sure this makes complete coherence to you because 1 is less than 2 and 4, 3 is between 2 and 4, and 5 is greater than 4. Hence, we've got this form of a tree now. So how many more numbers do we have to insert? 6 and 7. So now I'll insert 6. Okay. Now this is okay. Now 7. This is where the biggest problem of our life is going to come. So here we have a big headache. We're going to do a lot of splitting. So listen carefully. So now we're going to have 2, 4, 1, 3, 5, 6, 7. So now if we send 6 to the middle, now we can send 6 to the parent. But this time the parent's again going to overflow. So that's going to cause us a lot of problems. So first let's do that step. 2, 4, 6, 1, 3, 5, 7. So 1 is less than 2, 3 is between 2 and 4, 5 is between 4 and 6, 7 is greater than 6. So right now we have a major complication because this does not fit the standard we've set for the 2, 3 trees. So now what we do is we take a very clever approach. What we did here, when we had the parent overflowing, we're going to follow a similar approach. We're going to again explode the parent and break it down into children. So what we do is we're going to take 4 and then we'll put 2 on one side, 6 on one side. We'll put 6 on one side and then we put 5 and 7 like this and 1 and 3 like this. So when you find an algorithm to keep on doing this recursively until you finally get a simple tree like this, it's balanced, you can access this in log n time. So that solves the problem and we don't have a horrible tree like this anymore. This tree is very, very horrible for all practical purposes. For example, if you have thousands of children and thousands of nodes, then this tree is horrible. Instead, we have this tree which is really, really cool because it's quick to access and awesome. Thank you.